Alright, so we're taking the derivative f prime of x is 2 cosine. The derivative of cosine of 2x. How do we get that? Emma, do you know? Cosine of 2x.
Negative sine 2x.
Okay, negative sine of 2x times 2, chain rule. Okay, so it's minus a negative sine of 2x, and then you multiply by 2 because we got the chain rule here. Okay?
But then that equals the little note on the bottom, 2 sine x.
Yes. Okay, so now, does everyone see how we got this derivative first of all? Okay? This stuff is not going away, so if you're still struggling with this, you need to come and get some help, alright, with the trig function ones and the chain rule. Now this, in order to find critical numbers, we've got to set it equal to 0, alright? So, to solve this, this is where our stuff from last year comes into play. We have 2 cosine of x plus 2 sine of 2x. And you guys know from last year that you cannot solve trig equations when the angles are two different things. Alright, you can't have a cosine of x and a sine of 2x, so we need to make those be the same thing. Alright, and that's where, like William pointed out, we have this handy dandy note on the corner here to remind you of your double angle formulas. Okay, so we have 2 cosine x, and that's plus 2 sine of 2x. Now sine of 2x is 2 sine x cosine x. So this is a 4 sine x cosine x. Okay? So we took this right here. We used our identity over here. And we combined it with the 4, or with the other 2, to get that 4 sine x cosine x. And I'm going to get rid of that because that just made it hard to read. Okay? So, 4 sine x cosine x. Now we can solve, because all the angles are the same, we just factor out, on a pen. Let's factor out the 2 cosine x, and we have a 1 plus 2 sine x, sine x. Okay? So this tells us that either cosine x equals 0 or sine of x equals negative 1/2. And now it's all unit circle. Don't be surprised if this is given to you on something where you can't use your calculator. Alright? This is unit circle. So where does cosine equal 0? Cosine equals 0 at pi over 2. And 3 pi over 2. Good. Sine is a negative 1/2 at 7 pi over 6. And very good, 11 pi over 6. Okay? Yeah.
I, like, in a couple steps above, like, where the 2 cosine x or sine x cosine x, I just set one side equal to the other and then divided by cosine.
That's like if you had the equation x squared minus x and you took the x the other side and divided by an x. You're losing answers, and technically you're dividing by 0. Because 0 is a root. Cosine x, as we see here at the end, cosine x equals 0. So if you're dividing by cosine,
If I subtract it, it would be like negative 2 cosine x equals 4 sine x.
Yes, but then you divided by cosine, right? Well, cosine x equals 0, so you just divided by 0. Okay, so that's why we don't want to do that. You want to factor and get your answers this way. Now, another thing we want to do, it doesn't really make a difference here, but as we go on and we're looking at intervals where we're increasing and decreasing later on this week, we want to make sure our critical numbers are in order from smallest to largest. Okay? So what's the smallest of those? Pi over 2. And then the next biggest one is 7 pi over 6. That's just past pi. Then the next one is 3 pi over 2. And then, of course, 11 pi over 6. If you have trouble with that, just change them to have a common denominator. Pi over 2 is 3 pi over 6. And 3 pi over 2 is 9 pi over 6. And now it's easy to put them in order. Okay? So, or just visualize your unit circle and where those angles are, and that'll help you put them in order too. Okay? So now we have 0 on one end, 2 pi on the other, and now we just have to evaluate the function at all those points. Okay? For sake of time, I'm just going to fill them in, and we can make our analysis here. Okay? So at 0, what are we plugging these values of x into? The original function, okay? So this is f of x equals, so we have negative 1, we have 3, negative 3 halves, negative 1, negative 3 halves, and negative 1, okay? Now, as you look at this table, where is our max point? Okay, it's the point pi over 2, 3. Okay, the max is the point pi over 2, 3. Where's the min? Okay, so guess what? Here's one of those cases we mentioned that is possible where we have 2 absolute minimum points. Okay? The only way we have 2 absolute minimum points is if they are equal in their y value. So in this case, yes, we have 2. One is at 7 pi over 6, and the other is at 11 pi over 6. Both of these are absolute minimum points. Mins are 7 pi over 6, negative 3 halves, and 11 pi over 6, negative 3 halves. Okay? Get used to writing your max and mins as points. Alright? Your extrema are points. Okay? Does that make sense? A little bit of review from our last lesson. Okay? But that brings us to a little bit of an exploration. Okay? I want you to sketch something there on your paper. Okay? And I want to look at a closed interval. Okay? So here, everybody go ahead and draw yourself. Guys, go ahead and draw yourself a coordinate plane, and we're going to label the points 1, 3, and 5, 3. 2, 3, 4, 5, 3. Okay? So do this on your own, and I want you each to draw yourselves any function, but look, it says using a pencil or pen, draw the graph of a differentiable function of f. Okay? A differentiable function of f. So go ahead, draw one. You gotta get off your phone and get with this, okay? Come on. You have no clue what we're doing right now because you're on your phone. So I'm seeing a lot of different functions here, okay? And you know, a lot of yours looked something like this. You know, you had some curves in there. All right. So let's think about this question. And I actually want to use a little routine to help us answer this and address this idea here. Is there at least one point on the graph for which the derivative is 0? Okay? In this drawing there is, right? Because like here, the derivative would equal 0. And here, the derivative is equal to 0. But do you think that will always be the case?
Did you just draw a straight line?
And it is also there. It has also 0.
Okay. That's a great question, and that's a good answer, okay? So let's think about, we're going to use something I want to try to use as kind of a routine in here, and that is a claim support question. All right, so we're making a claim here that yes, and rather than writing it all, again, yes to this question, okay? Now, the support could be all of your drawings, because every one of your drawings had one, okay? But what's some other support here? Can you explain why you think that would have to be true, William?
Because the y coordinates are the same, no matter, like, you're gonna have the same end beginning y coordinates, so eventually, even if you draw like a straight line, it's gonna be 0. It's 0. So, yeah.
Okay. So want to add to that, Harrison?
Equals 0 is 1 point.
Okay, that's what we're saying. How would we prove it, basically?
Like if you had like 3.1 as the next one, then you can make a straight line. It won't be, you can't have like a derivative of 0 there if you have a straight line. But
Okay.
if you have like the same y coordinates, then it's always going to be something other. It's always going to be, you're always going to have a derivative of 0 at some point.
Okay. So if I'm understanding you correctly, I'll kind of draw it on here. We'll zoom in a bit. If this point were any higher or any lower, I could draw a straight line, and that would not have a derivative equal to 0 because it would be increasing, or it would be decreasing, right? But if I started increasing, let's say I started going up, but I have to end on the same y-coordinate, what's going to happen?
Decrease.
Go down.
I'm going to have to decrease, and wherever I start to decrease, I'm going to have a max point, which means the derivative equals 0. Okay? If I started going down at first, in order to end up over here at this point, I'm going to have to come back up somewhere. And wherever I decide to do that, I'm going to have a min point. Okay? So there's some support for that. We could do it in words. We could do it with the drawing. Okay? But then some questions you guys came up with, even before we got to this point. All right? What are the questions that could happen? All right? What about just drawing a straight line? Well, Melissa answered that. That's going to be a horizontal line, right? and the slope equals 0. So of course, the derivative would be 0. Okay? What are some other questions?
Can the graph be can it not be continuous?
Okay, there's a question, Terry. What if it were not continuous? In other words, we had this requirement that it had to be differentiable. Okay? So what if it wasn't a continuous function? Let me draw it again, like down here. Here's 1, 3, and 5, 3. So let's say it's not continuous. What if I drew it maybe going like this, and then there was like an open point down here, and it went like this? Does the derivative ever equal 0 on that interval? No. Okay. So one question would be, does it work? Does our theorem work if it is not continuous? And the answer is no. Now, does that mean you could never get one? No. It's just saying this theorem, or this claim, I should say, that we have to have at least one point where the derivative equals 0, would not work if it didn't have to be continuous. It's possible we could have one, but it wouldn't guarantee that there was one. Okay? The other question that you might come up with is, what if it's continuous, but not differentiable? Now, what would that look like?
A sharp point.
Yeah, a sharp point. Okay, so let's draw this again. So let's say that our graph looked like this in the middle. Something like this. It's kind of a cool looking graph. All right. Does the derivative equal 0 anywhere on that interval? No. Okay. Because what's the derivative at that point? Huh? Yeah, the derivative right here is undefined. Okay? So we're able to change direction from increasing to decreasing, but it's not at a point where the derivative equals 0, it's at a point where the derivative is undefined. Okay? So, this is why we had that requirement that it had to be a differentiable function. Okay? Because no to both of these questions. Alright? Now, all of this is to introduce the theorem that we just kind of discovered here, we kind of illustrated, and that is what's known as Rolle's theorem. Okay? Rolle's theorem. Rolle's theorem says that f is continuous on a closed interval from a to b, and it's differentiable on the open interval from a to b. Okay, so the only place it may not be differentiable is at the endpoints. Okay? If f of a equals f of b, in other words, the y-coordinates are equal, just like the one we looked at, there is at least one number c in the interval from a to b such that f prime of c equals 0. Alright, so what you guys were observing is actually our theorem here. If it's differentiable and the y-coordinates are the same, then somewhere in the middle there's got to be at least one point where the derivative equals 0. This is another one of those existence formulas, or theorems. It's proving that something exists. Okay? Now, we can illustrate with something that we've used in the past, or something we're familiar with, a parabola. Okay? So we're going to prove that f prime of x equals 0 at some point between the two x-intercepts. Okay? Now, x-intercepts have the same y-coordinate, right? Their y-coordinate is 0. Alright, so let's get our interval here, first of all, by finding the x-intercepts. If I factored this, I'd have x minus 2 times x minus 1. So my x-intercepts are at 2, 0, and 1, 0.
It's 3, 0. That looks like a 3.
Oh, sorry, that's a comma. 2, 0, and 1, 0. Okay? So the interval I'm looking at would be what?
1 to 2.
Okay, the closed interval from 1 to 2. Okay, that's my interval. So now let's think about f prime of x. F prime of x would be what in this case? 2x minus 3. There we go. 2x minus 3. If that's going to equal 0, that happens at 3 halves. Okay? Is 3 halves in the interval from 1 to 2? Yeah. Okay? So, yeah, 3 halves is between 1 and 2. So that is an example of Rolle's theorem. I knew there had to be some point in there, and now we found it. Okay, it's the point 3 halves, whatever that is. I believe it's negative 3/4. Yes?
Isn't this what we were doing before?
Yeah.
What do you mean?
Is it the same thing, or is it different because we first have to find the x-intercepts? Like.
Are you talking about the intermediate value
Yeah,
theorem?
squeeze.
No, like yesterday, what we learned was that just this without. Was that just giving you random intervals, and this is like intervals where. Like, what's the difference between?
Yes. Okay. Yesterday we were looking for a max or a min point on a closed interval. Here we're trying to figure out if the derivative equals 0 on a closed interval.
Okay.
Okay.
So this isn't saying that like every critical point is not, the derivative is not 0 at the critical point. That's not what it says. Because it seems
No.
like here we just use the same thing to find, same formula that we did yesterday to find the critical point.
Well, we found the critical number here at 3 halves. And yeah, if you remember, critical numbers are one of two things. They're either where the derivative equals 0 or where the derivative is undefined.
Okay.
Okay? So you have a critical number here at 3 halves. That's where the derivative is 0, and it happens in the interval
Okay.
we said it was. We didn't have to make them x-intercepts. We could have said, show that the derivative equals 0 at some point between the 2 points where y is negative 3
Okay.
or 5. This doesn't go down to negative 3, so.
Thank you.
Yeah. Okay. Here's another one just as an example here. Here we're given the interval. Okay. And we're going to illustrate Rolle's theorem here by first of all, it says find all the values of c in the interval from negative 2 to 2 such that f prime of c is 0. Well, how do we know any of these points exist? Well, if we found f of negative 2 that would be negative 2 to the fourth minus 2 times negative 2 squared. That's 8. And if I did f of 2, I'd have 2 to the fourth minus 2 times 2 squared, which is also 8. Therefore, I know by Rolle's theorem, there's at least one point between negative 2 and 2 where the derivative equals 0. Does that make sense? Okay? So I know for a fact that at least one will exist. Now what I can do is I can go ahead and find it. F prime of x is 4x cubed minus 4x. If I factor out the 4x, I get x squared minus 1. And notice here, where will that equal 0?
0
In one half.
0 and where?
One half.
and square root 1.
Square root of 1, which is plus or minus 1, right? It's a long day. Plus or minus 1. So 0 and plus or minus 1. So notice there are all three of those values are in the interval. So in this case, there happen to be 3 of them. Rolle's theorem told us there would be at least one of them. Okay?
I think that's what like I'm wondering is about. What when you plug in the 2 and negative 2 get 8, how is that telling you that there's at least
Well, because if you think about our graph here,
Oh, because they're both 8, because the y has 8 at both of them, so you know that. Okay.
yep, we have, just like in the example that we started with in the exploration there, we have 2 points that are horizontal to each other. So we know there's got to be at least one point.
So when you plug in the x values, you have to get the same y values in order for you to say that there is. 'Cause, like,
When you plug in the x's, you have to get the same y's, yeah. So this is going to look something like this. And at negative 1, 0, and positive 1, we have derivatives equal to 0.
So we don't have any extra ones besides these 3, right?
Not in this interval, no.
Okay, so what we are going to do is is x equals 0.
Well, when the derivative equals 0 is when we get our critical numbers.
So that's the critical
Okay.
number, okay.
Yeah.
Oh, okay.
Again, this guy's, and I know it's kind of strange to think of it this way, but this is just one of those theorems that's called an existence theorem. It's proving that something exists. It's not like it's something that's necessarily going to give us an answer, it just tells us that an answer exists. Okay? And that's why it's sometimes hard to understand exactly what it's saying. Okay? Alright.